Hi again for everybody. Now I will follow with my second presentation about neutron scattering. So first, why neutrons are good? Because neutrons can tell us where are the atoms and how atoms are moving. So X-ray also can say how where are the atoms, but they show different atoms. But neutrons also can tell us what they are doing. So in 1994, two people got the Nobel Prize for work in neutron scattering. Clifford Chall made experiments on antiferromagnetic sample, and he could prove that there are magnetic structures inside the sample even if outside there is no macroscopic magnetism. And Bertram Brockhaus got the Nobel Prize to build an instrument called triple axis spectrometer, which was able to visualize the excitations in a crystalline materials. We call it phonons. And since that, I mean, from the very beginning, the field of neutron scattering was increasing a lot until today's. Now, neutron scattering practically is used in all of the area of material science. Let's see what are the differences between neutron and X-ray scattering. So the basic of the scattering is just looking with a quasi-classical viewpoint. So neutrons are scattered on a potential. It's mostly the nuclei of the atoms, sometimes the magnetic field. X-ray causes a charge oscillation, and this charge oscillation will emit another X-ray, and that's what we call X-ray scattering. Using the quantum mechanics, there is a much better rigorous description, but this quasi-classical description is enough for showing the differences. So the scattering is with neutrons. By neutrons, the scattering is on the nuclei, and X-ray is scattering on the electron density. And the scattered intensity is isotope dependent for neutron. So we can see small elements as well, and we can see the different isotopes, while X-ray scattering intensity goes with the z square. The penetration depth is some centimeter in the material. For neutrons, for X-ray is much lower than a millimeter. The energy of the beam we use, I just selected the 1 angstrom wavelength beam. For neutrons, it's 81 millielectron volt, while in X-ray that's 12.4 kilo electron volt. So that's the reason why I say that with neutrons we can see thermal excitations, because that 81 millielectron volt is very close to the normal thermal energies, and we don't need 10 to minus 4 relative resolution in energy to see something. But the brilliance of the sources, for neutron, let's say it's a unit. For X-ray, it's at least 10 to 10 unit. So that means that with X-ray, you can measure almost everything. There are some things what you can't measure with X-ray, then you have to go to a neutron source. And the atomic scattering factor. For neutron, it's isotropic because neutron is scattered on a nucleus, which has 5 order lower radius than the wavelength of the neutron we use. But the X-ray intensity is decreasing in backscattering. And later I will show you why. There is no miracle in it. But that's a fact. So what, neutron doesn't matter. There is an absorption. We will hear it in the next presentation. And there is a scattering. It can be elastic, where the energy of the neutron doesn't change, and inelastic, when the energy of the neutron changes. That means that there is an energy exchange between the neutron and the sample, which is a condensed matter. We describe the interactions with the cross-section. The microscopic cross-section is the barn, which is 10 to minus 14 square centimeter, which gives the number of interaction within a secondum per unit intensity of 1 nucleus. There is the macroscopic cross-section, which is measured in 1 over centimeter. It describes the sample, and it depends on the nuclear density. Somehow it is missing. Oh, no, it's here. So the nuclear density times the average microscopic cross-section is the macroscopic one. So it speaks about the structure of the sample. So just a very few words about absorption. Generally, in the neutron energies we use, the isotopes follow the 1 over V rule, which means that the absorption cross-section is strongly increasing with the wavelength or decreasing with the speed. And there are a few exceptions. It's gadolinium and cadmium, which has a so-called resonance peak at the thermal energies, and for thermal neutrons it has a very high cross-section, and epithermal and faster neutrons doesn't see practically anything, so it's like a glass. Neutrons can go through. And there is a scattering. This is the topic of this talk. So the neutrons are scattered on the nuclei. The interaction is a short range interaction. As I told, it's a femtometer range. We describe the scattering by B. It's a scattering length. It's measured in femtometer. And this tells us the amplitude of the wave function which is scattered by the given nucleus. So now if we are speaking about B, then we are not speaking about intensity, we are speaking about wave function, the wave of the neutron, actually the scattered wave of the neutron. In the case of X-rays, as I told, B is not just a number, it's a B theta, where theta is the scattering angle, so it's highly scattering angle dependent. And the scattered intensity is given by the scattering cross-section, which is just 4 pi times B square. For neutrons, B can be negative, which means that during the scattering there is a phase change, actually with the pi, and it can be also complex if the nucleus is the high absorber. So let's look at what's scattering amplitudes are for X-ray and neutrons. As I told, the neutron has isotope sensitivity, so we can see different isotopes. X-ray is going with the square, and neutrons scattering length is roughly random as we go up with z, and it can change very lot within one element at the different isotopes. What we see here at the hydrogen, this yellow big circle is the so-called incoherent scattering. I will speak a little bit later about it. And these green and black spots are showing that the scattering length is negative. There is not too much isotope which has negative scattering length, but there are some, and we can use it for isotope substitution. Neutron is also scattered by the by the magnetic field, because neutron has a magnetic moment. So the component of the magnetic field which is parallel with the neutron spin, that gives an extra potential field. So the neutron can have higher or lower energy depending on the spin direction and the magnetic field direction. But during the scattering, the component of the magnetic field which is perpendicular to the neutron spin, that will cause a spin flip. So if we polarize the neutron with in one spin state, then during the scattering we can measure a spin flip scattering, which will give us information about the magnetic field or perpendicular to the neutron spin. And magnetic scattering happens only when the scattering vector is perpendicular to the direction of the magnetic field. This can be shown here if the scattering vector q, oh, it should be a bit later. Okay, so the neutron comes in with a wave number, it goes out with a scattered wave number, and the difference is the scattering vector, which is the q. And if the magnetic field is perpendicular to it, then we see the change. We see the magnetic scattering. If the magnetization is parallel with the q, this is a magnetic atom, then the neutron, which will be scattered at different positions, will see different magnetic fields, and that will be averaged. So in this case, we will not see magnetic scattering, only nuclear one. And since the magnetic field is large, I mean much larger than the nucleus, then magnetic scattering or magnetic scattering on an atom is not isotropic anymore. It is just like the X-ray scattering, so we will see a decreasing intensity as we go to the larger scattering angles. And there is also coherent and incoherent scattering. Coherent scattering means that after scattering, the neutron can make interference with himself. Here we can see what is the interference. So if two waves are in phase, then we see a large intensity. If the two waves are just in antiphase, then we don't see nothing. Here is a famous two-slit experiment. Here we can see the interference fringes and how the intensity is changing after two-slit if we have a coherent source. But there are incoherent scattering when after the scattering the neutron is not able to make interference with itself. So in that case we see a flat background like scattering. It has no structure. But we can use it. We can use it to look at the position of one atom. We can calculate the smearing of one atom, especially for hydrogen, because it's very weakly bounded. And we can see the energy levels of one atom if we are making inelastic neutron scattering. While with coherent scattering, there is an interference, so we can see the relative positions of different atoms, and we can see collective excitations. For example, phonons or magnons. A phonon is a mechanical oscillation in the crystal lattice. Magnon is spin oscillation or magnetic field oscillation in the magnetic materials. So how neutron is scattering on atomic structures? Let's have a beam that is coming in. It's a plane wave because the source is very, very far. So even a spherical wave can behave like a plane wave if we are far from the source, because the curvature is simply negligible. Then the neutron is scattered on the atoms. Here we have two atoms, and in one direction, also again very, very far from the atoms, we look at the interference. And the neutron scatters on one atom, goes towards the detector and scatters on the other atom, but the two atoms are in different positions, so the incident phase is differing. And also, looking back from the detector, this incident phase of the scattered the scattered phase will also change, and this phase change can be written as I wrote here. So there is the Ki times R. If this is the 0, then here Ki times R is the phase of the direct beam, and the minus Kf times R is the phase difference at the detector from the scattered beam. And we can rewrite it by writing QR, where Q is the momentum transfer. So this is the wave number of incident neutrons, outgoing neutrons, and Q is just the difference between them. And what we see, the wave function will be just the sum of the scattered waves with the given phase. So B is the scattering amplitude, and this is the phase change. And in a shorter form, here we see the scattered amplitude. So in scattering experiment, not only in neutrons but also with X-rays, electrons, and so on, the scattered intensity is always measured as a function of Q, and we call the Q space as a reciprocal space. In some old publications, one can see that X-ray measurement is shown as a function of 2 theta, which is the scattering, but that's a very, very old and obsolete notation from the time when people used mostly copper K alpha radiation. So the wavelength was fixed at 1.5 angstrom or something like this, and then you could calculate directly from the scattering angle this scattering vector. But nowadays the wavelengths can be changed, so only the Q which can gives us information. The scattered intensity is the absolute square of the wave function. So we cannot see the wave function itself, we can see only the intensity of the neutrons. We will never see the phase of the neutrons. And that causes some problems. So let's see how an elastic scattering is working. In the case of solid state samples, that's 99% of scattering events. So the neutrons come in with a momentum vector with k and scattered with a k prime scattered momentum vector, and here is the q. In this case, it's really easy to calculate the q because we have a nice triangle, and we can write down that 2k sinus theta is equal to the q. We use it in diffraction, small angle scattering, and reflectometry. But neutron can gain or lose energy. In this case, the ki is given, but the scattered wave number is changed because there is an energy change in between the neutron and the sample, and the energy change means that the speed of the neutron will change and the wavelength of the neutron will change, and k is 2 pi over the wavelength. So k can change, and at different energy changes we will see different momentum transfer, both in absolute value and both in directions. So inelastic scattering is a little bit more difficult. And in this measurement, we see a 4-dimensional space. So we are measuring as in a Q space, in the reciprocal space, which is 3-dimensional, and we are measuring also the energy change. This kind of scattering is very weak, and it needs very large measurement times. So, what we see after a scattering, that first is that we will see only the phase change of the neutrons, which is described by Q times R. And without mathematics, I try to visualize what happens. Let's get this 7-legged boot and walk away with 2 pi over q steps, and we are looking down and we are looking the surface, and in our head we make an average. And in average, if we step over always a valley or a mountain, then there will be a scattered intensity. And the size of these valleys and mountains will give the intensity. But if there are fast changes, like trees, we will not see them because we are looking at the average, and the trees are always in different places. So if we wanted to see the intensity from the trees, we need a smaller step. Smaller step means higher Q. And if we are just walking with the normal boots, then we will not see the mountains because it's the change will be very, very small within one step, but we will see the molehills, for example. With much more smaller steps, we will see the grass. And there is an inverse relation between the real and reciprocal space. So at large Q, I mean small steps, fast changes are dominant. So we can see atomic resolutions, or in our example, we can see the trees and molehills. At small q, we have this 7-legged boot, And we don't see the trees, we don't see the molehills, we see only the mountains. In scattering, we see only the nanoparticles that we call small angle scattering. There is one example, for example, a diffraction. We have a lattice spacing in a single crystal where the unit cell of the single crystal is just repeated infinitely. And what we see, if we have the right steps perpendicular to the lattice plane, then we will see at a given point very high intensity and nothing else with other steps. This is an example, this is a real measurement on an antiferromagnetic sample. It's not a very clearly visible measurement. These red spots are the Bragg peaks, and this sample was in a cryostate and also in a magnet, which has a lot of aluminum in the beam, and these circles are just coming from the isotropic aluminum which is in the beam. But from a single crystal measurement, we will see such peaks in the Q space as we do the measurement. What happens if we have larger particles, not atoms, bit larger or smaller wavelengths? So if the wavelength is comparable to the scattering particle, then we can divide the particle to smaller parts and calculate the same scattering from this smaller part. And if the neutron comes from the left, goes to the right, then here we can see the simulated wave function. It is just the real part of the wave function. In forward scattering, every wave is added in phase because there is no phase difference. So the phase difference from the incident beam is just the same but opposite as the phase difference of the scattered beam. So forward scattering is always large, but backward we see a decreasing intensity. Here is it's not easy to see, but looking at the intensity here we can see that forward there is a high intensity, backward there is a low intensity. This is exactly the case of the atomic scattering factor of X-rays. So that's why X-ray has scattering angle dependent scattering factor, because X-ray is scattered on the electron density and the atom has much larger size than the nucleus, and it is already comparable with the X-ray wavelength. If we have even larger particles where the wavelength is already smaller than the particle itself, then we see practically nothing at backscattering and very weak signal on the side. We see only forward scattering, and that's the case of small angle scattering when we want to see large particles with smaller wavelengths than the particle itself. In this case, we will not see the structure of the particle inside. This is what I said, that we see the hill, but we don't see the trees and the molehills. Here in the front we put the detector, and we will see the particle itself only. And that's good, because it's the atomic structure will not disturb us. So what are the properties of the scattering function? At small q, as I told, we don't see the atomic structure, so we can use the scattering length density, which is just the average scattering length in a unit volume, and then the wave function is a so-called Fourier transform of the sample. But we don't see the wave function, we see the absolute square of the wave function. So we will see the so-called autocorrelation function, which gives the similarity between the sample if we push it just a little bit further. And this autocorrelation function will be Fourier transformated, and that's what we that Fourier transform what we will see. For example, from a Gaussian, if we have a Gaussian distribution, after in the autocorrelation image we will see 2 times larger variance, so square root 2 times more wide Gaussian distribution. And if the sample has many different components, then the scattering intensity it is not just the sum of the intensity coming from the components, but also the correlation between the components. So we will see the relative positions also of the different components. And the scattering function of a lattice with a d lattice constant will give the same lattice with 2 pi over d lattice constant, as I showed you in the previous example in diffraction. And the scattered image of a Gaussian distribution will be Gaussian, but the variance will be inverted. It's 2 over sigma square because this 2 comes from the autocorrelation, which just doubles the variance. So if somebody is good in Fourier transform and convolution and so on, then very fastly I just tell you that the Fourier transform is the Fourier scattered wave function is the Fourier transform of the sample. What we see is the absolute square, and using the convolution theorem we will see that the intensity is the Fourier transform of the scattering length distribution convoluted with itself, and which is the autocorrelation function. And if we have a convolution or a structure of similar particles, let's say ρ1 is the particle and ρ2 says the structure of these particles, and then the intensity will be the product of these two theoretical intensities, and this is the same backward. So if we have a structure which is just a product of 2 functions, then we will see the convolution of the two intensities. Okay, let's see some more example about these functions I was speaking before. So if the sample has a structure of the same units, this is like a crystal which has a unit cell which has some atoms, for example, but this unit cell is repeated, so it's a real single crystal. Then what we will see the product of the intensities. So this is our original lattice. This blue lattice would be the original reciprocal lattice. So these are the Bragg peaks from our crystal, But this one element, this is I call unit cell, it has a scattering function of this green curve, and the original lattice will be multiplied with this green curve. That means that the Bragg peaks, intensity of Bragg peaks, will be changed by the unit cell itself. So we will have smaller, larger intensities. We can have also forbidden reflections, which means that there should be a Bragg peak, but we doesn't see anything. And what happens if our system is non-ideal? For example, we have random displacement in a periodic system. We have our lattice, but the lattice is not at 0 Kelvin. It has a movement. Each atom is moving randomly. And this effect will not increase the peak width, but it will decrease the peak height at large Q. Why? Because our nice position distributions, this blue one, will be smeared by the thermal movement, and then finally we will get a decreasing function. So it's a kind of convolution, the original lattice and the thermal movement, which will cause a multiplication. So we get the original lattice multiplied by the Fourier transform of this Gaussian, which is this green, and we will see a continuously decreasing Bragg peaks. This is what we call the Bivolar effect. This is the same backward. So if we have a finite crystal which has not too much unit cell, and we can describe it, for example, as a infinite crystal multiplied by a Gaussian, then our beautiful sharp Bragg peaks will get broadened, and that means that we will not see anymore these very sharp peaks. That also means that if we are measuring the width of these peaks, and it is larger than the resolution of our instrument, then we can say what is the size of the crystallites what we want to measure. And this is called as a Scherrer equation. Oops, why is it here? Yeah, this was the end of the kinematical scattering, which works also for X-ray and neutrons and electrons and so on. And now a little bit show something about instrumentation. In the case of neutrons, the monochromators are of high importance. So we can monochromatize the neutrons, I mean select one wavelength using a single crystal, using the Bragg scattering. In this case, the single crystal reflects only one wavelength, which goes to the sample, and then we can see the diffraction. For this, we can use pyrolytic graphite, silicon, or germanium, and for smaller wavelengths, the Copernical is better. But we also can make time-of-flight measurement, which means that we chop the beam, or as I told you before lunch, that we can have a pulsed source as well, and then the neutron starts with a very sharp peak and flies away. This is a so-called time-of-flight diagram. As we go farther, the faster neutrons arrive sooner here, the slower arrive later here, and with time measurement we can determine the wavelengths and the wave number. For that we use neutron choppers. They are just big aluminum plates with a hole somewhere and absorber everywhere else, and it's rotating, and when these disks open, then the neutron can go through. When it closed, then here, for example, then the neutron cannot go through. This is the base of the time of flight measurement, and we can use velocity selector. This is a lot of strain chopper where after each other the neutron enters on one end, and this selector is continuously rotating, and the neutron with the good wavelength can survive and come out, and with the wrong speed, if the neutron is faster, then it will be catched by one of the wall, and if it's slower, then the other wall will hit and absorb it. So that's why we call it velocity selector, and this gives much worse resolution. It is mostly used for small angle scattering, but worse resolution means that it gives much higher intensity. And I show some instruments. For example, diffractometers. That's a single crystal diffractometer, a monochromatic one. Here the reactor wall is here, and within the shielding there is the monochromator which selects the wavelength. The same diffraction can be done by using time-of-flight. This is our TOF instrument at the Budapest Research Reactor. Here we have pulse shaping chopper and other choppers which just avoid the overlapping of different beams, and then the scattered beam is measured mostly at backscattering to have high resolution, and we are just measuring the flight time starting from here and arriving to the detector in this way. Here the chopper produces the pulses, and we have a relatively large wavelength band. That means that here the measurement can be done mostly in one setup. Meanwhile, in single crystal diffraction, in monochromatic diffraction, many times we have to move the detector to change the measured Q range. And sometimes we have to change also the monochromator angle to change the wavelength. And there is the inelastic scattering. In inelastic scattering, we have to somehow monochromatize also the scattered beam, because we are interested in the change of the energy. So there is a monochromatic beam arriving to the sample, and we monochromatize the scattered beam. There are some possibilities to do. The first one is the triple axis spectrometer or three axis spectrometer, where the neutron beam is monochromatized by a single crystal, and the scattered beam is monochromatized by another single crystal. And this is the instrument of Bertram Brockhaus. That's why not exactly this one, but but the base of inelastic scattering, the base of triple axis spectrometer was written down by Bertram Brockhaus, and that's why he got his Nobel Prize. There are other inelastic spectrometers, like the direct time-of-flight spectrometers. Here the incident beam can be monochromatized either by time-of-flight, so we have a pulse shaping chopper here and the pulse shaping chopper at the sample, and then a monochromatic beam will arrive to the sample, or we can use also monochromator here. But what is highly needed is the so-called monochromatic chopper just before the sample, because it makes a small pulse, and the scattered beam will fly from the sample to the detector, and in this case we are measuring the time from the sample to the detector, and from this flight time we will see the energy of the scattered neutrons. The time of flight diagram, again, it's the length, it is the time, is looking like here. That's a so-called TOF instrument. Here we have a monochromatic beam. We produce it with choppers. There is the sample here, and the sample scatters inelastically, so the neutron can come out faster or slower, and we are measuring this distribution as a function of time, and we change it as a function of energy. And just finally, one example how we can use both X-rays and both neutrons. This example is measuring protein structure. This is an extremely huge protein, single crystal. I think it's lithosim. Generally, the crystals that can be measured has a 200 micron, something like this, and this is larger than a millimeter. And we can see a lot of Bragg peaks from it. It's a single crystal, but the lattice spacing is extremely large. It's some 100 angstrom, which means that the lattice distance in the reciprocal space is very small, so that's why we see so many Bragg peaks. This is similar with X-ray and neutrons. What's the difference? That with X-ray we see the carbon, oxygen, nitrogen, everything which is not hydrogen, and we can do this measurement in a minute. Actually, I think this crystal is even too large for an X-ray measurement. And we know almost everything. But if the protein has some very important hydrogen, and the protein function depends on the hydrogen position, then that's what X-ray doesn't see. So then we can put this sample into the neutron beam, going to the ILL, and make a 1 week measurement. And after this 1 week measurement, we can localize the hydrogen. Not exactly, so we will not see points that here is the hydrogen, here is the other one. We will see just a smeared position because the hydrogen is weakly bounded. But we will see the distribution of the protons around the main structure of the protein itself. So the two measurements together gives a very reliable measurement. So along with neutrons, it's really difficult to get the total main structure. Along with X-ray, it's really difficult to get the hydrogen positions, and together we will see everything. And I think that was my last one. I was a bit late, sorry for that. But thank you for attention, and if somebody has questions, then please ask me.